want to talk to you really quickly about something called complex conjugates. If you have a complex number, a plus bi, the complex conjugate of that number is a minus bi. Now where this becomes really interesting to us and where this starts doing something for us is, okay, that wasn't a good idea. If we need to if we multiply a plus bi and a minus bi together, just like multiplying any other pair of complex numbers, you use the FOIL method or double distribute. A times a is a squared. Outer two terms would be minus a times b times I. Inner two terms would be plus a times b times I. And the last two terms will be minus b squared I squared. So your middle two terms are going to add together to give you 0. I squared, of course, is always negative 1. So we got a squared minus b squared times negative 1, or a squared plus b squared. You'll notice there's no imaginary part to that number, so it's just a real number. And so what's kind of cool about complex conjugates is if you multiply them together, you get a real number answer every time. For example, let's say we've got 2 plus 3i is our number, and we're going to multiply that by the conjugate, 2 minus 3i. You can simply learn the pattern. This is the first term multiplied by the first term. And then we've got a plus, and it's b squared, which is the last number. So if you recognize that these are complex conjugates, you can think of this as 2 squared plus 3 squared. And go straight to 4 plus 9 is 13. Now if if you don't remember that, certainly you can multiply it out. Two times 2 is 4. 2 times minus 3 is minus 6i. 3i times 2 is plus 6i. 3 times negative 3 is negative 9. I times I is I squared. So you're going to end up with 4 minus 9 times negative 1. 4 plus 9 is 13. But you don't have to do the multiplying it all out and showing all those steps if you learn the pattern. When we have division problems with complex numbers, a lot of the times they're going to be written like this example is written, and where it looks like a fraction. You just need to remember that that fraction bar means divide. So in this example, we've got 5 plus 4i divided by 4 minus I. Now you kind of treat this the same way we did expressions fractions with square roots in the bottom, where we really are kind of offended, for lack of a better way of talking about it, by this I that's in the denominator of this problem. To get rid of I in the denominator, we can make that happen if we multiply that denominator by the complex conjugate, 4 plus I, which is fine as long as we remember to do that to the numerator or the top of the fraction as well. And now it's just a straight multiplication problem. 5 times 4 is 20. 5 times I is 5i. 4i times 4 is 16i. 4i times I is 4i squared. In the denominator, we're going to end up with 4 squared plus 1 squared. So simplifying, 20 plus 21i, adding the two terms in the middle, minus 4. And then on the bottom we have 16 plus 1. So 16 plus 21i all divided by 17. Or if we're going to write that in standard form where we have a real number part separate from the imaginary part, we'd have 16/17 plus 21/17 times I. So anytime you see a division problem involving complex numbers, think about multiplying by the conjugate of the denominator. One other thing that I want to show you real quickly are some tips for simplifying expressions that have square roots. Basically, whoops, do over. All right, so simplifying roots. The thing to keep in mind is that you want to simplify each root first. Before you think about adding like terms or combining like terms, simplify the roots first. I'm going to make a big deal of that because it doesn't necessarily, it's not always what you see that you think of to do first. But it's the only way that you're going to get the right correct answer in the end. So, for example, we've got a square root of negative 27 plus a square root of negative 48. Negative 48, there we go. Okay. So we're going to think about that as negative 9 times 3 under the first radical and negative 16 times 3 under the second radical. The square root of negative 9 is 3i, and then the 3 stays under the square root. The square root of negative 16 is 4i, and then the 3 stays under the square root. Now we've got like terms that we can add. 3i plus 4i is 7i times the square root of 3. Now that becomes a little more, simplifying the roots first was kind of logical in this problem. There is nothing else that you could possibly do other than simplify the roots. But with a problem like this, where you have negative 2 plus the square root of negative 3 all squared, you do kind of have a choice. Part of me wants to think about squaring this binomial before I simplify the square root of negative 3. But to get the correct answer, we need to do that first. Pull out I, because that's really all we can do with that one. And now multiply negative 2 plus I times the square root of 3 times itself. Okay, now notice we are not multiplying complex conjugates there. So you actually have to work it all out. Negative 2 times negative 2 is 4. Negative 2i times square root of 3 is the outer. Negative 2i times the square root of 3 is the inner. And then we've got 3i squared. Square root of 3 times square root of 3 is 3. I times I is I squared. So cleaning this up, 4 minus 4i times the square root of 3, the two terms in the middle are like terms. 3i squared is negative 3, so 1 minus 4i times the square root of 3 is the way to go there. Same thing in this last example. We want to simplify the square roots before we even think about doing anything else. So we've got negative 14 plus the square root of negative 12 over 2. So negative 14, let's see, plus, I'm thinking of negative 12 as negative 4 times 3. So negative 14 plus 2i times square root of 3 is all divided by 2. Now I'll divide 2 into each term. Negative 7 plus I times the square root of 3 would be the correct final answer.